Good evening, everyone. We are excited to present our analysis and redesign of a cordless power drill. This is Group 23's presentation. Let's get started. A cordless power drill is a portable tool used in construction, woodworking, and home improvement to a few applications. Some key features include a battery, variable rotation control, and an ergonomic design to fit a wide range of applications. Market for these tools is over $20 billion worldwide. Massive growth is forecasted, with primary and secondary customers featuring professionals, enthusiasts, and businesses. In this slide, we have an exploded CAD model of the cordless drill. All components can be categorized under the shell, power supply, or a rotation. This slide visualizes the exploded view of the CAD model.
To start off, we conducted a fast diagram analysis, which helps us break down the cordless drill into the main functions. These main functions were identified as rotating a drill bit and holding a drill bit. A functional component mapping matrix was then constructed to understand the impact of redesign and potential for creating a product platform due to modularity. Functions were further analyzed to identify which ones differ when creating a variety of product offerings. Combined with a component comparison table, we identified the battery, gear assembly, chuck assembly as areas to derive product variety. Design alterations were explored for the modules. First, we looked at gear assemblies to vary speed and torque for different applications. Secondly, we looked into a keyed chuck to go with the keyless chuck, offering more compatibility with accessories. Lastly, we considered high-capacity batteries to cater to customers that require heavy use from their cordless drills. Product family assembly diagrams were then constructed to show the potential variety and opportunity for delayed product differentiation. Assembly diagram 2 delays branching to the fourth step in comparison to diagram 1, which branches on the first step.
For the design for manual assembly, based on the cord chart, drill shell and gearbox will fall into high functional importance category, and assembly time is also larger for gearbox. Gears is from the module selection and drill shells are from the platform selection. We have selected gear housing and its cover for the design for manual assembly, and in the earlier design it is difficult to align gearbox and cover for fasteners, so we have eliminated them and reduced the part count. To assemble them, we have added threading for ease, and it is reducing the assembly time also. As you can see, this is approximately reducing assembly time by 20 seconds. We have opted gear assembly for the DfM. Gearbox consists of different parts, and in the gearbox all the gears are based on the standard dimensions, and gearbox to chuck and motor to gearbox are already optimized according to DfM Pro. So we have choose to work on housing cover and housing. Cover and housing is the solid part, and mass is in the range of 0.028 to 0.0495, plus the batch size is 5 lakhs unit, and so there are only two suitable processes. One is powder methods and another one is machining, so we have opted for machining. In the DfM Pro, there was recommendation to use standard hole dimension, and also sharp corners were around the threading area. The hole's location is near to the edge for the cover, so we decided to provide threads instead of fasteners, but in that also there were sharp corners. So in the last modified design, rounded threads were used. In addition, instead of taper angle for the housing, we have used without any taper angle, plus holes are of standard dimension only. After the DfM, there has been reduction of cost by 14% via analytical method and 58% via hubs. The difference between these two values can be due to data used for the calculation, which can be old.
We optimized the operation process by improving part selection and design. Initially, the process included multiple fasteners and 4 injection molded parts. After implementing snapfits, we reduced the number of paths to 2, eliminating 10 fasteners. The change significantly cut assembly time by 61% from 173.93 seconds to 166.97 seconds. The redesign improved efficiency and minimized complexity during manual assembly. Introducing snapfits eliminated fasteners, reducing overall assembly time from 92.55 seconds to 6.6 seconds, streamlining the assembly. This slide focuses on part selection for automatic assembly. The total assembly cost for each part ranges from low for the motor at $0.34 to high for screws at $6.21. Using a functional important matrix, we prioritize high importance items like the gear assembly, chuck, and motor, while minimizing costs for low importance items like screws and the nameplate. This approach streamlines production and reduces overall assembly costs efficiently. This slide highlights improvements in automatic assembly design. By following DFA guidelines, such as reducing part count, fasteners, and part variety, we consolidated 5 enclosure parts into 2 by eliminating the nameplate, drill palm, and drill shell top. This simplification significantly reduced the assembly costs from $20.75 to just $4.47. These changes improve efficiency, streamline production, and lower manufacturing expenses.
Moving on to selecting the best manufacturing process for ABS thermoplastic drill shell casing. We evaluated methods based on material compatibility, shape, mass, section, thickness, tolerance, and batch size. Machining and injection molding met all the criteria. Other methods like blow molding and thermoforming failed the key requirements such as section thickness and tolerance. Additive manufacturing lacked viability for mass production due to limited batch size. Injection molding was chosen for its cost efficiency, making it ideal for large scale production. This slide provides a concise comparison of DfM Pro recommendations for drill shell design before and after DfM process. On the left, we have recommendations for the old drill shell design, which includes increasing the minimum radius of the feature and also reducing the depth to diameter ratios of the hole. On the right, we have modified drill shell design, which incorporates key improvements. The inclusion of snap fits replaced traditional fasteners, simplifying assembly. However, these changes introduce unavoidable undercut formation in the design, a trade-off to enhance assembly efficiency and part integration. This slide shows cost and design improvements achieved through design for manufacturing process for the drill shell assembly. For each part, the DfM process resulted in significant redesign. While the material cost remained unchanged, operating and tooling costs increased due to improved features and integration. The total cost per assembly rose from $0.6 to $1.2. However, this increase is offset by reduced part count, simpler assembly, and improved manufacturability. We eliminated 10 fasteners by introducing a snap-fit assembly, which streamlined the design and assembly process. The DfM guidelines utilized during the process are as follows. By consolidating the total number of injection molded parts from 4 to 2, we have achieved a design that is easier to manufacture and assemble, despite the increase in per part cost. This slide summarizes key improvements from DfM analysis for the drill shell assembly. These changes demonstrate effective use of DfM principle, balancing cost with improved performance, scalability, and streamlined manufacturing.
Product service systems integrate sustainability and customer focus. Use battery collection with discounts, promote recycling. Interactive app tutorial and dedicated support enhance user experience. Maintenance is simplified with on-demand scheduling and IoT-based predictive alerts. Flexible subscription models offer short-term rentals, easy repair, battery recycling, and model upgrades, ensuring value and sustainability. Design for assembly and design for manufacturability strategies led to significant improvements in efficiency, assembly time, and cost reduction. Automated DFA reduced cost, while DFM for gear assembly improved both cost and time. Although DFM for drill cell increased cost, it improved manufacturability and reduced part count. Revisiting the design would focus on cost effective assembly.